Well, how's everybody doing out there? Well, welcome to day 26 of Corona Online School and Thanksgiving week. So today we're going to finish up chapter 11. So this is a kind of a good way to go into Thanksgiving break. So we're going to be talking about different types of symmetries that can occur in the plane and tilings and things like that. So let's kind of jump right in. So I just mentioned here that symmetry comes up all the time, kind of what makes things look pretty. So we've got some definitions of symmetry here. So let me flip over to the slide so you can see the definitions. And so if you want to, you can write the definitions in first or whatever. So a symmetry is just any rigid motion of the plane that moves all the points of a figure back to the same points of the figure. And so we're going to talk about a couple different types of symmetry here. So the first one we want to talk about is what's called reflection symmetry. So in this case, symmetry across the line of reflection or a mirror line. So this would be our mirror line, this dotted line. And so the mirror line divides it into two pieces, which are mirror images of each other. So the idea is if you were to take this mirror line and use that as the folding point of a piece of paper, then this thing would just lay right on top of the other. So again, go ahead and kind of write that down in your notes. So hopefully there was enough. Hopefully you saw both of them. So, and then let's go back. And then here's a practice one is having you go through and try to figure out, first off, how many lines of symmetry each of these have. So a figure can actually have more than one line of symmetry, so that's kind of nice. And so go ahead and draw in the lines of symmetry, and if there's four, draw in all four of them and stuff like that. So at this point, pause the video, work on practice one, and then when you're done, come back and we'll talk about a different type of symmetry. All right, so hopefully everybody did a good job, got all the different lines of symmetry that's available. So now what we want to talk about is what's called rotational symmetry. And so let me flip back to the slide, other definition slide here. So rotational symmetry is the figure completely overlaps itself when it's rotated through a certain angle between 0 and 360. The center of this is called the center of rotation. So in this case, it's hard to see, but this dot here in the middle would be the center of rotation. And then with rotational symmetry, since it, we want to know how long it takes to get back around, then what we have is what's called the order. So a shape has rotational symmetry when it still looks the same after the same number of rotations of less than one full turn. The number of positions at which it looks exactly the same gives you its order. So for example, like in this case, if we rotated this kind of 90 degrees, this yellow would be at the top. And then if we rotated it another 90, now the yellow would be over here. If we rotated another 90, the yellow would be down here. And then finally, if we rotated it the last 90, then the yellow would get back to the beginning. So since it took 4 rotations, it still looks the same at each turn, but since it took 4 rotations, that tells us the order in this case. So with this one, the triangle, so this is kind of the same thing. So to go from here to here, we would have gone like 120 degrees. And then this would now be the yellow. So again, go another 120 degrees. This would now be the yellow. And then the final 120 degrees, and then we're back to the beginning. So again, 3 turns did that for us. So hopefully, if you remember these were 90, hopefully you recognize some kind of pattern between the angle and the order of these figures. So kind of keep that in mind when you're doing the practice problems and stuff like that. So let's jump back to the practice. So in this case, we've got find the order and the smallest angle for each of these guys. Oh, let me talk about the last definition at the bottom, but oh, you don't want to do stats. I assume not. So, and so point symmetry is rotational symmetry that's exactly 180 degrees. So in other words, a rotational symmetry of order 2. So in this case, for me to get from here to here, like it's going to be a 180-degree rotation. So again, from here to here, 180 degrees. So it has to be 180 degrees exactly, and it has to have rotational symmetry of order 2. All right. So if we go back, so that's going to be the last question. It's at the very bottom there. So again, look at these figures, find out what the order each of is, what would be the angle of rotation for each one, and then finally at the very end, I'm going to ask you about the point symmetry. Does any of them have point symmetry, and which ones? So at this point, pause the video, work on rotational symmetry, and then when you're done, come on back and we'll talk about something else. All right, so for practice 3, this one is trying to figure out which types does it have. So the nice thing about a figure is it can have rotational symmetry and reflection symmetry and point symmetry, in fact. So in this case, that's what you're trying to do, decide all the different symmetries that each of these have. So go ahead, pause the video, work on practice 3, see if you can figure out all the different symmetries that these different figures have. And then practice 4 and 5 has you guys actually trying to draw polygons that meet certain rules and stuff like that. So work on that. And then when you're done, unpause the video, and then we'll come back and talk about the final topic, which is tiling. All right, so hopefully everybody did a good job being able to notice the difference between the different symmetries, being able to identify which ones were which and stuff. So now what we want to do is talk about what's called a tiling, or tiling of the plane. And so, and you've seen again probably this every day. So like if you have a brick house, or if you've driven by a brick house, like the way all those little rectangular bricks are put together, tiles like the side of the house, well, the side of the house would actually be the plane. Or if you have like tile in your kitchen floor or something like that, same idea. So in this case though, we're going to be tiling stuff with all kinds of different shapes, which makes it kind of nice. So let's first talk about, what is a tile and a regular tiling. So let me jump back to the definitions here real quick. There we go. So a tiling, well, tile is just a different shape. And so a tiling is a simple closed curve together with its interior. A set of tiles forms a tiling of a figure. Figure is completely covered without overlapping. And so a cool tiling is what's called a tessellation. So I don't know if you've actually ever seen these or not, but if you are a fan of MC Escher, he's an artist. Like he has some beautiful tessellations that he's made where he's tiled a plane with some, really, really remarkable type figures like lizards and all kinds of weird stuff. So you guys are actually going to be making your own tessellation as part of a project. So this should be fun for you guys to work on. So this is just a sample tiling with obviously triangles that we've used in this case of different colors. And so a regular tiling is a tiling where the tiles are regular polygons of one shape. So in this case, since it's regular polygons, then that means we're looking at like equilateral triangles, squares, pentagons, hexagons, things like that. And so it turns out, and we're going to see this in a second, whoops, we're not ready for that, that not every regular polygon can actually form a tiling. So that'll be kind of important to recognize. So in this case, like I would have you guys do this in class with different polygon tiles. So what I want you to do is take different polygonal tiles, pattern blocks, to determine which 3 regular polygons could be used to form a regular tiling. So we can't use the polygons or the blocks, but there is a nice little app called Pattern Blocks by Matthews that you can download and look at. Now the only downside is it doesn't give us all of the regular polygons, which is kind of unfortunate. So, but the ones it gives us allows us to make a tiling. So for example, if I take this equilateral triangle, and then this one, let me rotate it. Whoops, too far. Notice how these guys fit together perfectly. There's no gap, anything like that. And I could do this forever. It would take me a long time to tile this big plane area. But you can see how these guys join together and make no gaps. Then clearly a regular polygon or an equilateral triangle would do a good job at tiling the plane. So that one definitely works. So a square is kind of a no-brainer. It definitely does the job. I mean, and so I can add ones down low, I can add ones above, and you can easily see that no matter what I do with these squares, they're always going to join up. They're always going to make a nice figure and stuff like that. Unfortunately, I don't have a pentagon on here, but a pentagon doesn't work, and so it's too bad they don't give you the pentagon figure so you can try it out. So, but if I go up to the hexagon, the hexagon works perfect. Like, it does a good job of tiling. And it turns out that's it. That's as far as we can go. So this is kind of like those platonic solids where there's only certain, like, 3 possible choices. So in a platonic solid, we had pentagons, triangles, and squares were the only thing that could form platonic solids. Well, in a tiling, the only thing that we can get are triangles, squares, and hexagons in this case. So pentagons don't work, and anything bigger than 6-sided is never going to be able to tile the plane as a regular polygon. So jot that down, so that's kind of a good thing to know. So those are going to be the 3 answers at the bottom. So we're looking at equilateral triangle, our square, and our hexagon. So those are our only possible choices in this case. All right, now if they're not regular polygons, you can do all kinds of stuff. So kind of keep that in mind. So this means they all have to be the exact same shape. So you can do tilings with mixed shapes, and we'll practice some of that, because like I could put some of these guys in here like this. Possibly, we'll see if I can make it work. So, well, I don't know if I'll have a slim triangle figure like that, but it's possible that you can combine different shapes together and make a tiling. But for a regular tiling, we're looking to just use one and only one shape. So keep that in mind. All right. So a vertex figure, let me go back to the slide. Oops, I don't know why I keep wanting to teach you guys stats today. So a vertex figure is an arrangement of a bunch of different polygons together that all meet in a common vertex. So that's kind of the key here. So in this case, we've got the green shape is a dodecagon, so a 20-sided, or let's see, 12-sided. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12-sided, sorry. We've got 2 equilateral triangles, and then we've got our square. And so this big blue or big purple point is that common vertex for each one of them. And so in this case, like, what makes this work, what allows you to have a vertex figure, is all related to these angles. So if you imagine that circle as the dot as the center of a circle, then we know what angle does all the circles equal up to? 360. So if we flip to the next side, that's going to be the key. So the only way you're ever going to form a vertex figure is you have to make sure that the sum of all the angles equal 360. So in this case, the angle of the dodecagon, so this angle here, is 150. The angle of each triangle, since they're equilateral triangles, are each 60. And of course, the square is 90. So again, you can piece these together all kinds of different ways, like lots of different shapes, but you still have to have that magic number of 360 in order for this to actually work. All right, so let's go back so we can work on our own figure. So in this case, do 6 equilateral triangles form a vertex figure. So again, what I would do is I'd recommend going to the Mathies app. And let me clear this whole thing out. And just try it and see what happens, so you have to rotate these guys so they match up. And see if you can actually form 6 triangles around some center point there and see if it actually works. Could you do 4 squares around a common point? So that one's kind of a no-brainer. But yeah, you can see right there. So this is kind of similar to what we were doing when we were trying to make three-dimensional shapes when we were actually trying to form the platonic solids. So remember, we couldn't put four squares together because it made a flat. So what we did for platonic solids is we put three squares together and then folded them up, and that's what made our half of our cube. So in this case, we're actually trying to go that next step in trying to form the flat. So how many of these triangles, how many of these shapes can we put together before it becomes flat? So keep that in mind. So again, this is kind of related to our platonic solids. All right, so we're going to practice 7. Practice 8, this is trying to make your own unique figure. So again, it would help to use the Mathies app, so that way you can kind of see what it looks like. And if you want to just like take a picture or something like that and put it in, or try to draw it, that would be fine. And so can do two equilateral triangles, a regular hexagon, and a square, form a vertex figure. So again, use the Mathies app, try to put them together, see what you come up with. And then finally, the last two things that we want to do excuse me, or try to tile the plane with some of these irregular figures. So in this case, we've got a trapezoid, and then in this case, draw any kind of scalene triangle that you want. So it could be acute, it could be obtuse, it could be right triangle, whatever, and then use it to try to scale or tile the plane. So remember, you may have to rotate this thing and stuff like that in order to get it to work, but ultimately you should be able to fill up this whole dotted area with these different shapes. So for the collaboration, I'll have you guys post your different tilings, your different vertex figures, stuff like that, so we can kind of see what you've come up with. So otherwise, good luck, and if you have any questions, I'll be around the computer all day. So see you later.